We're going to start this switching section actually with a history lesson, and it's a short one. It's about hubs and repeaters, and these are two devices that if you never touch one in a production network, you're not going to really miss anything, and you'll see why here in a few minutes. The reason, first off, that I include them in this course, you are going to see them on your CSENS and CCNA exams. You need to be able to compare them to switches, what they can do, what they can't do. While you might see them in a production network one day, the real reason you need to know this material is that it shows you really where we've been and why switches can do some of the things that repeaters and hubs can't do. And let's just dive right into that with repeaters and hubs. First off, these are layer 1 devices. They are considered physical layer devices because they're really not going to do any kind of switching of any kind. They're really just doing one thing. And with a repeater, what are we repeating? What is that one thing? Why are we doing that? Well, you know the deal with the radio station. As you're driving out of a city, if you're listening to a station, that signal starts gradually breaking up as you get further and further away from the station. It's not like you hit a certain distance from the station and it just stops totally. It just starts breaking up a little bit and a little bit and a little bit. And that gradual weakening of the signal, it's called attenuation. And that happens to any electrical signal, which includes the ones and zeros that we're sending across our media. We talked about a couple of maximum effective cable lengths being 100 meters. Well, let's say we have two hosts that are 175 meters apart. Well, that's going to be a problem because the signal is going to be strong when it leaves the transmitting host, but it's either going to be extraordinarily weak when it gets to that other host, or it could just be non-existent. In that instance, it probably would be. Because again, it's strong when it leaves, but then it weakens as it goes across the media, and then finally it could be very weak and practically unusable when it gets to the destination. That's the problem that repeaters helped us resolve, because a repeater takes an incoming signal and then generates a new clean copy of that exact signal. That's all a repeater does. Now, a hub really operates in the same fashion, but the hub has more ports. That's really the only major difference between the two. A hub is a multi-port repeater. Now, some of you may be saying, well, I've worked with smart hubs, that can do a little bit more than that. That is true, but a basic hub is simply a multi-port repeater. So again, we were at this time, it's like, hey, we're never going to need anything better than this. Life can't get any better. Well, why did we need switches anyway? Why did we ever need anything better than a repeater or a hub? And to answer that question, let's see what happens when a hub is in the middle of a simple little 4PC network. Do notice that there is a single double arrow on top of this hub. I would be ready to recognize that for a hub on the exam. Don't count on the fact that Cisco is going to tell you, because they might not. Now, this simple little setup illustrates two problems with hubs. First off, using a hub here means that only one PC can send data at a time. And if that sounds like a bad idea in today's networks, you're right, it is a bad idea in today's networks. Didn't always work great in yesterday's networks, but it was certainly better than nothing. What we have here is one giant collision domain. And that means that the data that one host sends can collide with data sent by another host. And the result of that is that all the data involved in the collision is unusable. So we've already got this collision going on. That sounds bad, and now you would think the hosts have to retransmit that data. But what if they just keep both retransmitting and we just keep having collisions? That wouldn't have been good for us. So what we came up with, well, what someone else came up with, I'm not going to take the credit, but what they came up with is carrier sense multiple access with collision detection. Quite the mouthful. And thankfully it's referred to as CSMA-CD. And here's that process in action. If a host wants to send data, and again this is on a shared Ethernet segment, if a host wants to send data, it does what we call listening to the wire. And all it's doing is seeing if the shared media is in use. Does it detect a signal that indicates that another host is sending data? If the media is in use, the host is going to back off a few milliseconds and then listen to the wire again. If the media is not in use, as you would expect, the host then sends the signal. Now, if two PCs happen to do that at the exact same time, the voltage on the wire actually changes. And it indicates to both of those hosts hey, you know that stuff you just sent on the wire, it collided with somebody else's stuff. So now we have a data collision. Well, the PCs that sent that data now generate what we call a jam signal. And that indicates to the other hosts on the shared media that they shouldn't send data right now. Now, the PCs that sent the data will then invoke a back-off timer set to milliseconds. And when each host's random timer expires, they will each begin the CSMA CD process from the beginning where they listen to the wire. Please note that whenever a device is going to send data, it's always going to listen to the wire first, even if it's a retransmission. Now, that back-off timer value, it's totally random. So it's highly unlikely that the two hosts are going to have the same problem again. Now, this entire process happens pretty quickly. We're talking milliseconds here. But of course, it would be much more efficient, I'm sure you'd agree with me, to have no collisions at all. That's what we really want. Because the collisions slow down the overall network, and then you've got to retransmit again. You've got all these little delays built in. And as I like to say, those little delays add up to a big delay. Now, the ultra delay sensitive traffic that networks have today, voice and video traffic, delays due to collisions and retransmissions, I mean, that's totally unacceptable. And that's another reason you won't see many repeaters and hubs in today's production networks. Now, that's all bad enough, but that's just to deal with collisions. We have another big issue with hubs and repeaters, and this one has to do with broadcasts. Just as that network we looked at is a single collision domain, it is also a single broadcast domain. And I know if this is new to you, if the terminology is new, that sounds like a good thing. Oh, I've just got one broadcast domain. I've just got one collision domain. Actually, you want as many as you can get, because what you're doing is localizing the impact of any damage, and you're also cutting back on the waits. And when I say about the time and the waiting, every single time a PC on that hub sends a broadcast, every other PC on the hub is going to receive a copy of that broadcast. It's actually flooded out, even if that PC doesn't need or want the broadcast. And those other three PCs that are receiving it, they still have to look at it, they still have to unpack it, they still have to say, oh, I don't want that, I don't need that, and then throw it away. And again, all those little extra hits of time and to our overall processor, they do take a toll. So we really want to limit those. And again, here's that one PC sending a broadcast, and all of the other PCs attached to that hub are going to get a copy of that broadcast. Now, there's a reason that we don't go home after any kind of class or you've read a book or anything and take everything in that book and apply it to your network. And it's because that everything we do on a router or a switch has a cost. That's why every Cisco router in the world doesn't run every feature that they possibly could. Because if you don't need it, you don't run it. And everything we do has a cost. And I don't mean a financial cost. It's a cost in time. It's a cost to our bandwidth, our available bandwidth. It's a cost to our available processor power. Now, you might look at this drawing and say, well, really, what's the big deal? Does it really matter? Well, it would matter a lot if, say, we had 63 more devices connected to that hub. Let's say we had a 64-port hub. That means that when a device sends one broadcast, 63 copies are going to be made and be sent out to those other hosts. And that's a real waste of our time. We don't want that. Because what happens is, and in the example I have on the board, 64 PCs attached to a hub, and let's say that 3 of the other PCs ever need to get a broadcast sent by one particular PC. Well, that means the hub's got to create and send 60 unnecessary copies of the data. And that means that every PC that doesn't need the broadcast still has to look at it because they don't know if they need it or not until they actually look at it. That's really the key. And of course, the bandwidth. The bandwidth required to send 60 unnecessary copies adds up pretty quick. Now, it's a great idea to limit the scope of our broadcasts. This is something that we come back to a couple of times throughout the course because what we don't want to try to eliminate broadcasts. We want to limit their transmission to hosts that actually need them. But right now, I just want you to see between the possible data collisions and the unnecessary propagation of broadcasts, hubs and repeaters have serious limitations when it comes to today's networking. 2 devices that can help us with those collisions are bridges and switches. Now, switches, I'm sure you've heard of. Bridges, maybe not. So we're going to talk about those for a few minutes in the next video and then head off into switching. So I will introduce you to bridging on the next video. See you there.